Welcome everybody. So today I'm going to talk to you about intermolecular forces in detail. We're going to discuss the different types of intermolecular forces and then how each one plays out. So the first type of intermolecular force isn't really an intermolecular force. It's more of what happens when you have a mixture, a solution. And that type of intermolecular force is called an ion dipole. And with the ion dipole, what you get is this attraction between an ionic compound that's dissolved into water, for example, a polar molecule, and how these interact. And so what you can get is something to the effect of this, if I show you. So you could have your water. And your water has these partial charges. It has, a negative charge and a positive charge. And then you have your ion. And so if I were to draw on my ion for this, if I move my water down here just to put it in the center, if I were to show my ions involved with this, I would have my positive sodium ion interacting with the oxygen, and then I would have my negative chlorine interacting with the hydrogen. What's interesting about this is that you actually can form something called a hydration shell, and that's a case where the waters will surround it, and you get something that looks kind of like this, where we have our waters surrounding the ions, and you get these interactions, these hydration shells. And so this happens a lot with ionic compounds. It happens less so when we have, two polar molecules mixed together. Then we wouldn't form these molecule-ion interactions. So now what if I have just a pure substance? What if I have just, a polar compound or water, a very polar compound? Different types of intermolecular forces appear, and let's take a look at those. So the first type of intermolecular force is called a dipole-dipole. And a dipole means polar molecule. So this is a situation where you have two polar molecules, and they attract each other. And, the thing that happens is when they get together, they form a liquid. So, if I were to have, a polar molecule here with its positive and its negative, and I were to have another polar molecule here with its positive and its negative, they're pretty far apart. And if this was in the gaseous phase, the chances of them actually coming together and forming a liquid would be low. But as they move around randomly, and we can do that here, as we move them around randomly, when they get close to one another, they can start to attract. And when I move them close to one another and they start to attract to each other, then I can form an interaction between them, and I can get an intermolecular force that I can zoom in here and I can draw for you. And there's my intermolecular force. And so now I have this intermolecular force that has formed between these two. And now they formed a liquid. And so with this, what I see is that the more polar that the molecules are, the stronger the forces are between them. And this is important because the stronger that these intermolecular forces are, that equals higher boiling points. So we'll get higher boiling points when we have those stronger intermolecular forces. And we can see that if we have a list of, molecules in increasing polarity, like if we were, for example, to go from, something like, if I were to do HCl, and I were to compare this to something like HF. So HF is a more polar molecule than HCl. So the HF should form stronger forces of attraction. And those stronger forces of attraction should allow the molecules to stay in the liquid form longer. And when they stay in the liquid form longer, it means that they will have a higher boiling point. Now, regardless of if I draw HCl or HF, the idea behind their interaction is the same. If I were to have an HCl here with its positive and its negative poles, I could have another HCl over here, and I would have an intermolecular force that would form between them. Well, HF is going to look the same way with HF. Here's my HF with my positive and my negative. Well, here's another HF coming close to it, and you'll form that intermolecular force between it. The concept of intermolecular forces is the same. It's just dependent on how positive or negative the particles are. And if you look back at this page in the notes here, it says all intermolecular forces are based on partial positive and negative charge interactions, and that is true. We see that here with the positive negative ions interacting with the polar molecules with a molecule ion. We see that here where we have positive and negative attractions between polar molecules. Now, there is a case where you have really, really strong polar molecules. And when you have really, really strong polar molecules, you will form a special type of dipole-dipole. It's called a hydrogen bond. Before I show you a little bit about hydrogen bonds, though, this is just a diagram showing you a more complex representation of what the dipole-dipole interactions look like. You can see that there's these dotted blue lines over here that I'll highlight, and then there's the red lines here. The red lines are illustrating the attractive forces, and the dotted lines are illustrating the repulsive forces. The idea is to sort of maximize the attractive forces and minimize the repulsive forces, and that's what we're trying to do. Now, I was alluding to a hydrogen bond before, a special type of dipole-dipole. This is about, this is stronger than we see for the dipole-dipole. So this is an extreme dipole-dipole force. And that's really important to note. People think of hydrogen bonds as being something separate from a dipole-dipole, but a hydrogen bond is just a special type of dipole-dipole. It occurs when you have hydrogen in the compound, and it's bonded directly to a small, highly electronegative element like fluorine, oxygen, and nitrogen. Not only is fluorine, oxygen, nitrogen electronegative, but it also has a small radius. It's that combination that makes the hydrogen bonding possible. So if I were to look at this, some common molecules that have this, things like H2O. H2O's molecule that has hydrogen directly bonded to oxygen. Hydrogen fluoride, ammonia, and a lot of organic molecules having hydrogen bonding. Things like alcohols with the OH group. Things like amines with an NH2 group. And we'll talk more about these when we do organic chemistry, but we see hydrogen bonding in a lot of molecules. People, and biologists sort of came up with this, coined this phrase of hydrogen bonding, and the idea is because it's so important in biology. We look at hydrogen bonding and how it's necessary for water to be a liquid. Hydrogen bonding explains that high boiling point of water. We're mostly made of water. Without this hydrogen bonding, without this very polar nature of water, we would be, non-existent. We look at DNA structure. The idea of this base pairing, A pairing with T, C pairing with G in a DNA double helix, that comes from hydrogen bonding. Look at protein structure, secondary protein structure, how the protein folds has a lot to do with hydrogen bonding. So again, hydrogen bonding is just a very strong form of a dipole-dipole. Here are some illustrations of hydrogen bonding. So here's two waters, hydrogen bonded together in the top here. Here are two ammonias. Here's a water and ammonia mixture, and we show the different combinations of hydrogen bonds at the bottom there. What I find interesting about water in particular is we can look at solid water like a snowflake and we can see the crystal structure of it. And if we zoom in, we can see that that crystal structure is due to the idea that the water is forming this hydrogen bonding network. Hydrogen and oxygen bonded together, the bond is not as polar as hydrogen and fluorine. And yet we see that water has a higher boiling point than most other substances the same size as it. And part of that reason why that's the case has to do with the fact that there's two hydrogen bonds formed in every water molecule, and it forms this extensive network. And if you look at the diagram at the bottom here, you can see here's the covalent bond, the 1 angstrom distance. And then here's the hydrogen bond, the attraction between adjacent water molecules. It's longer, and it's less powerful than a covalent bond, but It's still there. It's still a strong type of intermolecular force. Okay, the last type of force is London dispersion forces, and this is the weakest type of force. And it's the weakest type of force mainly because it's happening between nonpolar molecules. So two nonpolar molecules, they don't have any force of attraction between each other. They shouldn't have any partial positive, partial negative. But what we see is that when they get close to each other, adjacent molecules, when they're in the vicinity of one another, they start to attract each other. And an interesting phenomena starts to take place. It's called polarization. This polarization, and I'll write this down here, this polarization, it is the point where the two particles start to distort each other's electron clouds. So this is called polarization. And that's where we have this distortion of electron clouds. This is also called an instantaneous dipole. It's where a dipole forms for an instant. And so if I were to have a diagram of this showing this happen, it would look kind of like this. On the left here, we have two nonpolar molecules, in this case two nonpolar atoms, helium. They're not attracted to each other. But as they come close to one another, the nucleus from this helium starts to attract the electrons from an adjacent helium. And those electron clouds get distorted. It forms this instantaneous dipole. This is like an on-off switch. It's polar for an instant, and then it becomes nonpolar. Polar for an instant, then it becomes nonpolar. It's going back and forth. And that sort of is the reason why this is so weak. What we see is that when the molecules get close to each other, the forces increase. And what we also see is that the bigger the molecules, or atoms, the stronger the London dispersion forces are. And so, for example, if I were to look at like F2, Cl2, Br2, and I2, I would see that the F2 has the weakest forces. It's the smallest. It has the least attraction to other F2s. That has the least chance of being polarized. They call it the least polarizability. Take a guess for if you were to go from helium down to xenon. What do you think would be the molecule with the strongest forces? What about the molecule with, or the atom with the strongest or highest boiling point? Let's talk about that tomorrow. Okay, so look, something important that, I want to just end here with the London dispersion forces. Even polar molecules have some London dispersion forces. The issue is that you don't talk about the LDFs in water because the hydrogen bonds are so much stronger. So these London dispersions are overshadowed. But at the same time, they still exist. And the AP exam expects you to know that. They expect you to say water has hydrogen bonding and London dispersion. They want you to mention the London dispersion. It's there. It's just weaker. Again, the LDFs, they're going to increase as we increase the size of the molecules. As the molecules get bigger, then you'll have a higher boiling point. Now, you can even have situations where the LDFs are strong enough that they're stronger than a dipole-dipole. A classic example is this, and I'll leave you with this one. Let's say that you had Cl2, and it was versus HCl, and I give you the boiling points. I say the Cl2 boiling point is let's say negative 50 degrees Celsius, and the boiling point for HCl is negative 75 degrees Celsius. And they ask you to explain this in terms of intermolecular forces. So I'm going to leave you with that question. See if you can come tomorrow to class with an explanation as to why Cl2 has a higher boiling point than HCl. Also, please take a second and look over the intermolecular force diagram here, and next time we'll do types of bonding in solids. All right, thanks so much for watching.